Hello all, my name is Grant, and this is Genomia, a Julia-based parallel processing genome assembler prototype for research here at Wayne State University. So what's the premise? Well, on Friday, I had a discussion with a PhD candidate here at Wayne State University, and he proposed a side project of a genome assembler. So first of all, what's a genome? A genome is a nucleotide sequence of DNA that consists of a long character sequence of letters from A, C, T, and G. Now, genome assembly will take parts of a larger DNA strand, such as this image here, and try to piece them back together. So, for instance, if you're in research and you're doing research on part of a strand, or you get part of a strand, you want to piece that back together. Now, in my discussion with this PhD student, I found out that personal computers often can't process large data sets efficiently, which, of course, and current assemblers often do not utilize parallel processing, which could make the process so much more efficient. So, what about the existing genome assemblers? Well, current genome assemblers can be split into two categories, long reads and short reads. Long reads have higher error rate but read longer sequences of data. Short reads have high accuracy, however they're really inefficient as they require a lot of reads for longer sequences. Additionally, our other competitor, if you will, in the scene is the Genome Graphs.jl library, which has great accuracy but does not utilize parallel processing and thus has rough performances. So real quick, I'm Grant. I'm a computer engineering sophomore at U of M. I'm not a biologist, so I consulted a lot of people for this project, and usually I use not Julia, so mostly C-based languages. So what's our goals for this project then? Well, we aim to create a Julia-based assembler that can handle large strings of input. Julia has built-in parallel processing handling, so that'll be simple. Additionally, Julia has been more prevalent in science programming recently, so we'll choose this language as opposed to C++, for instance. So we're going to start small, we're going to handle small data sets, and then we'll continue to larger sets. And then if we have time, we'll try to create a front end with Genie.jl, and then we'll connect the system to a database for data retrieval and storage, as this is an on-the-fly research tool, and we'd like to have easy input readability. This project had a lot of challenges. The connection with databases was really rough. I tried to use the oracle.jl library to connect to the Oracle database system. While the Oracle database system worked itself, the Julia connection did not work. Additionally, algorithm creation and accuracy is a subject we'll talk about soon. Lastly, feasibility was the biggest concern of this whole project. I bounced around with a lot of different ideas, and I was worried I was too ambitious after reading some online forum posts, but alas, here we are. So let's talk about the algorithm design, and we'll show off the program. So to complete an assembly, we're going to first do some short reads to k-mers. A k-mer, with k being an integer value, is a subsection of a sequence of DNA. As seen here, k equals 4, so we're going to take segments of 4 out of this larger sequence, and then we can split them up and compare, and we can piece them back together with 3 characters of overlap, if you will. Then we're going to assemble a De Bruijn graph, which is a directed graph that'll we'll just do what I just talked about, which is comparing the prefixes and suffixes. And then we can do an Eulerian walk later on to finish it off and create our full sequence. So yeah, let's talk about the code then. So we have 3 tests that I'd like to show you guys. First test, we have 3 pieces of data. This is from the earlier example in the slides, slide number 2. And what you'll see is we're going to use k equals 10 for this example. And you can see here that through the parallel processing function, which will open some threads for each k that we run, we're going to create the graph and we'll print it out, which you can see here, which is just a directed graph, and it's in adjacency list form. And then we'll find the start k-mer in order to start the reconstruction. And then we'll find an Eulerian path in this function, which will give us an array of nodes, if you will, in the graph and allow us to reconstruct it through reconstruct sequence, which will perform the Eulerian walk and then combine everything by appending the last letter of each node to the overall sequence. So as you can see here, this reconstructed sequence will match what is expected here for test 1. Test 2, for instance, now is just taking the individual strand itself and seeing if we can piece it back together from a set of uh, nodes, if you will. So what you can see here, of course, is the adjacency list, and then we piece it back together, and then this matches exactly as we see up here in the sequences. Lastly, I'd like to show an inaccurate test, which will show the flaws with our system, despite all the work we've put on it. Larger data sets, such as this, which has multiple strings into it, can vary widely with the k we input. Thus, we need to find a way to get a correct k every time in order to get the right sequence, because as seen here, k equals 11 just so happens to be the correct sequence for this large array of sequences. So this will be needed to tackle in the future. Additionally, in the Genomia folder, you'll see a rudimentary prototype of the UI system that I'd like to use for data input and output. Due to some changes with the framework, I was not able to deploy this in time. So yeah, what was built? Well, we built a highly efficient genome assembler with decent accuracy. It's weaker to larger data sets in terms of accuracy, but it's really efficient with the parallel processing of Julia. Additionally, we built a rudimentary front end for data inputs, which we saw earlier. So what did we learn? Well, we learned Oracle and its SQL and its database system. While it wasn't used, I did spend an awful lot of time on it, and that was a big time sink that didn't pay off. Additionally, we learned a lot more about bioinformatics. I don't come from a biology background, so this was a very interesting venture into uncharted territory, if you will. Additionally, we learned the De Bruijn graph and the algorithms that were needed to construct such a graph and then reassemble the sequences. That was very interesting. So what's next? Well, I'd like to incorporate a connection with the database. As mentioned earlier, we now know how to use Oracle database, but also we could use AWS through some packages that exist in Julia. Additionally, I'd like to improve the front end and improve accuracy, which would likely need consultation of professors and professionals. So thanks. I had a great time. I was able to explore different applications of CS in biology. And yeah, this was a very interesting project, and I hope that I can continue to go forward with building it. Thank you all.